Greetings viewers at home. I'm your host Masuku Bongani from Kangala TVET College, Mpondozankomo campus. So today we are going to look at Engineering Science N1. We are going to look at chapter number 4, which is heat. So now when we look at our slides, they are saying there, when we are looking at heat, we are going to look at heat and temperature. There it is shown that heat is a form of energy. Temperature is an indication of the degree of hotness or coldness of a body. Then now when we pass, we are going to look at the temperature scales. Now on the temperature scales, we are having two temperature scales. We are having basically, when we look at our slides, we are having the Celsius scales, and we are having the Kelvin scale, which is the thermodynamic temperature. Going forward, we are going to look at the conversion scale. Like for instance, we know that when our temperature is at zero Kelvin, when we look at our PowerPoint, we are having minus 273 degrees Celsius, which is our absolute zero. Then when we are having our 273 degree Kelvin, we are looking at 0 degrees Celsius, which is our freezing point. But at 373 Kelvin, that's where we are having 100 degrees Celsius, which is our boiling point of what? Our boiling point of water. Then we can come up with this, we can come up with the equation to say that when we are having T, which is our temperature in degrees Celsius, is equals to what? Is equals to T in Kelvin minus 273. So basically, we are using this equation to change from what? To change from Kelvin to degrees Celsius. Then vice versa, we are having what? We are having the following. We are having T is equals to T plus 273. Basically, we are using this equation to change from what? To change from degrees Celsius, which is this small letter T, to what? To Kelvin. Then with this takes us to our main focus of today. That's where we'll be looking at thermal expansion. We'll be looking at the specific heat capacity. Then now, this is what it is said. Under thermal expansion, this is what it is said. It is said that suppose we are having an aluminum rod, which is having its original length at room temperature L0, and now when we are having an increase in temperature, it is said that this aluminum rod will increase with a small millimeters. But these small millimeters in which our aluminum rod is increasing, it's so small such that we cannot see it with our naked eyes, such that we can say these small millimeters, we call it delta L. Then now, at the end, when there is a change in temperature, when the temperature rises, we can also find our what? Our final length, the original length of our what? Of our substance. This is whereby we add the total length from what? From L0 to what? To the change in length, we can say is our L final. This L final that we are having here is our total length after expansion. Then now, we are having what we call a decrease in temperature. This is what it is said, the theory behind the decrease in temperature. It is said that when we are having our aluminum rod, when there is a decrease in temperature, our aluminum rod will what? Will decrease in what? In length, which will result in what? In a what? A decrease in the what? In the original length. Then now, I want us to look at the following slides. This takes us, when we are looking at our PowerPoint slides, this takes us to the what? To the equation of thermal expansion, whereby we are having our change in length. We said is equals to what? Is equals to alpha, the original length, the change in what? The change in temperature. So now, when we are having this formula, what do we know? Let us look at our PowerPoint slide. We are having the following. We are having our delta L, which is our change in length. This is the small millimeters in which our, what? We said in this case, our aluminum rod. Our aluminum rod in which it is what? It is expanding. Then we have our alpha. Let us check our PowerPoint slides. We have our alpha. What is our alpha? Our alpha is the coefficient of what? Of linear expansion. What did we say about the coefficient of linear expansion? We said that it's a constant for each and every material. We can have water. We can have what? We can have, let's say, aluminum. The coefficient of linear expansion, it won't be the same. But now, under our what? Under our L1, here we said we are having our LO. Our LO is our original length, the original length of the what? Of the aluminum rod at what? At room temperature. Then we have our what? Our change in T. Basically, our change in T, we know that our change in T is equals to what? Is equals to T2 minus T1. Then now, what do we know about this T2 and T1? We know that this T2, according to this diagram that we have drawn here, we can just simply say this one is the final. Or we can say is the final temperature, T2. This one is the what? Is the initial temperature. Then now, with this, we are going to do what? Whatever temperature that we are given initially, which is T1, we are going to do what? We are going to minus it from the final temperature to get our what? Our change in temperature, which is the small what? Temperature. In most cases, it will be the small temperature in which our temperature is what? It's what? It has changed due to what? Due to expansion. Then now I want us to look at the following example. We are having example EXP, which is example number 1. Let us check on our PowerPoint slides. They are saying under example number 1, a steam pipe has a length of what? Of 2.5 meters at a temperature of 15 degrees Celsius. Steam which has a temperature of what? Of 235 degrees Celsius is what? Is passed through the pipe for several hours. If the coefficient of linear expansion of the pipe material is 12 by 10 to the power minus 6 per degree Celsius. What did we say? We said each and every material has its own what? Coefficient of what? Of linear expansion. Then now I want us also to focus on our PowerPoint slides. This is what we are having. We know that on our PowerPoint slide we are having our what? Our original length. We said our original length LO is equals to what? Is equals to 2.5 what? Is 2.5 meters. Then now our change, our what? Our change in temperature. Our change in temperature, it started with, when we look at our PowerPoint slides, it started with a temperature of what? Of 15 degrees Celsius and rise in temperature to what? To 235. Then now we can say our change in temperature is equals to, we can say is equals to what? Is equals to 200 and what? Is equals to 235 minus 15. Then now, with this, we got that our change in temperature is equals to what? Is equals to 220 degrees. what? Degrees Celsius. Then now, what do we have? We have our coefficient of what? Of linear expansion. What did we say about the coefficient of linear expansion? It's a constant for each and every material. In this case, our coefficient of what? Of linear expansion, we said it is what? It is alpha, which is denoted by 12 by 10 to the minus 6. But this one is what? The unit is 12 by 10 to the power minus 6 per degrees Celsius. Then now, since we are having our knowns, we can substitute to the original formula, but now we must keep in mind what did they requested in the question. They said we must calculate the increase in what? In length the pipe will what? Will experience the increase in what? In length. Then now, what are we looking for as the increase in length? We are looking for delta L, meaning now we have our original length, our temperature, we have our coefficient of linear expansion. Then now we are looking for our delta L, which is our increase in length, the small millimeters in which our steel pipe is increasing, which is what? It's unknown. Then now we can come to say, this one is our example number 1. We can come and say our change in length is equals to what? Is equals to the coefficient of what? Of linear expansion, the original length times by delta T. Then now what do we know? We know that the coefficient of what? Of linear expansion is what? Is 12 by 10 to the minus 6 multiplied by the original length at 15 degrees Celsius. We are given as 2.5 meters. Then we multiply it by the change in temperature. We said the change in temperature is 220 degrees Celsius. Or we can always write the units at the end. Then now with this, we got that our answer is what? Is 0.066 meters, which is equivalent to, because what did we say? We said this 0.066 meters is the small millimeters in which our what? In which our steel pipe is increasing. What did I say? Check this 0. You check this 0. Meaning we have 0.066. What did we say about this change in length? We said this change in length is the small millimeters in which our what? In which our steel pipe is increasing. Then now, these small millimeters in which our steel pipe is increasing, we said we cannot see it with our what? With our naked eyes. Hence, is 0.066 meters, which is equivalent to 6.6 millimeters. Then now, when we check at our question, we are going to check, let us check on our PowerPoint slide. The second question, it says, calculate the what? Calculate the final length of the what? The final length of the pipe. Then for the final length of the pipe, what do they want when they say calculate the final length at the pipe? Meaning they are requesting this final length. We are to add the what? The initial length plus the small millimeters in which our what? In which our steel pipe is increasing. One can say, let us just continue here for interest sake. Let us say this one is A. For number B, we are looking for our what? For our total expansion, which is our final length. Our final length, we are going to say our L final is equals to our what? Our L initial plus the change in what? The change in length. Then now, this is what we are having. Our L initial, we were given to be what? To be in the statement, we were given to be what? To be 2.5 plus. What is the small millimeters in which our what? In which our steel rod is expanding? The small millimeters is our change in length, our delta L. What is that delta L? We are given as 0.066, which is equivalent to 6.6 in millimeters. Then with this, we are getting our answer as what? as 2.5 what? 2.5066. This one is in what? This one is in meters. Then this one will give us our change in what? Our final length, our original length, when our aluminium rod has increased from what? From the original length at room temperature, which is what? Which is LO, to what? To a final length, which is what? Which is delta L. Then now, I want us to look at what we call the specific heat capacity. So now, when we are looking at our PowerPoint slides, it is said there that the specific heat capacity is the amount of energy required to rise the temperature of 1 kg of a substance, which is what? Which is 1 degree Celsius or 1 Kelvin. The amount of heat energy a substance gains or loses is proportional to the mass of the substance, the specific heat capacity of the substance, the type of material, the change in temperature of the what? Of the substance. So now this is what it is said. It is said, remember previously we were looking at what? We were looking at the coefficient, which is alpha. The coefficient of what? Of linear expansion. But now they are talking of the specific heat capacity. What is the specific heat capacity? Now we are talking of what? Of C. Let us have space. Now we are talking of the specific what? The specific heat capacity. All these constants, the what? The coefficient of linear expansion, the specific heat capacity, which is our C. We are having our what? Our alpha, we are having our C. This alpha and this C are constant. What did we say? In each and every material has its own what? Coefficient of linear expansion. Each and every material has its own what? A specific heating capacity. You must keep that in mind. I want us to look at the formula for specific heat capacity. We said that we are having what? We are having Q is equals to M. We are having MC, the change in what? The change in temperature. Then now, I want us also to concentrate on the PowerPoint slides. Our Q there, it's our heat energy in joules. Then our M is the mass of the what? Of the substance in kilogram. Then our C is the specific heat capacity of the substance. What did I say about the specific heat capacity of the substance? Is the constant, is different. Each and every own material has its own specific heat capacity. Then we are having our change in temperature. This change in temperature, what did we say? We said is T2 minus T1. Then I want us to look at the following example. They are saying in the following example, let us look at our PowerPoint slides. They are saying 58.5 kilojoules of energy is absorbed by a copper cylinder with a mass of 2 kg. The initial temperature was 20 degrees Celsius and the specific heat capacity of copper is 390 joules per kg degrees Celsius. You are requested to calculate the what? The rise in what? The rise in temperature. But now, before you can calculate the rise in temperature, you must have your knowns. First, you are having Q, you are having M, you are having what? C, you are having your what? Your change in what? In temperature. Then now, we need to find our knowns. At the end, the unknown will be the what? The variable that we are looking for. Hence, they said the rise in what? In temperature. We can all know, we can all see that they want the what? The change in what? In temperature. So now, let us check. This is what they are saying. They are saying now we are having what? We are having 58.8 what? 58.8 kilojoules, which is by 10 to the power 3 of what? Of energy in joules. Then they are saying there, the mass is what? is 2 kilogram. The specific heat capacity of the what? Or of this substance is what is given. What did I say? I will emphasize this, that the specific heat capacity of a substance is a constant for each and every material, which is what? Which is 390 joules per kilogram degrees Celsius. Then now we have our change in T. But our change in T is T2 minus T1. What is T2? Final temperature. Initial temperature. Are we together? Then now, this is what we are having. What are we having as our final temperature? It was said that this is why when we are looking at this, we can see that delta T is equals to what? Delta T is equals to T2 minus T1. Then now, we don't know T2, we don't know T1. What is said? We know that we are looking for what? For the change in what? The change in temperature. Therefore, the change in temperature is our what? It's our unknown. Then now, what is the question saying? It is saying calculate the what? Calculate the rise in temperature. What is the rise in temperature? Remember, is the smallest what? Temperature in which our what? In which our what? Our substance is what? Is increasing. Are we together? Then now, this is what we are having. We know that for our change in T is equals to what? Is equals to Q over what? MC. This Q is our heat, our mass, our specific heat what? Capacity. Then this one is what? Is 58.8 by 10 to the power 3 divided by, what is the mass? Is 2 multiplied by the specific heat capacity, which is 390. Then now, we found that our answer is equals to what? Is equals to 75 degrees Celsius. The follow-up question, let us look at our PowerPoint slides. It says, calculate our final temperature. We can say this one, it's A, number B. For our final temperature, what do we know about our final temperature? We know that our final temperature is what? Is T2 is equals to what? Is equals to T1 plus the change in what? In temperature. Then now, what do we know? We know that the change in temperature is 75. But what is our T1? Our T1, now we must know what is our what? Our T1. Our T1, it was the initial temperature, which was given as 20. Then this one is 20 plus this 75. Then we are getting what? We are getting 70, 80, 95. 95 what? Degrees Celsius. Then with this, it takes us to what we call our second part of what? Of heat, which is called the heat transfer in a substances that are in contact. Let us go back on what we did in previous grade. We said when we are having a closed system, in a closed system, we said there is no energy that can enter in that system. There is no energy that can do what? That can leave the system. So this takes us to when we are looking at substances or objects that are in contact. When we are looking at our PowerPoint slides, it is said that heat lost in a hot body is equals to heat gain in a what? In a colder body. So now, what do we see? Heat lost in a what? In a hot body is equals to heat lost in a what? In a hot body. This is what it implies. It implies that since it's a closed system, let us look at our PowerPoint slides. Since we are looking at our PowerPoint slides, we are going to have the following. We know that heat is M, what? MC, the change in T. This is what? This is what is heat of the what? Of the hot of the hot body must be equals to what? To MC, the change in T of the what? Of the cold body. So now this happens in when substances they are in contact. So let us look at the following example. They are saying after a steel component was welded, its temperature had risen to 850 degrees Celsius. It was quenched in a tank containing 30 liters of water with an initial temperature of 19.5 degrees Celsius until both components and the water reach an equal temperature, which reach an equal temperature of 25 degrees Celsius. Assume no heat lost and the specific heat capacity for steel and water is given as follows. We have for steel, which is 400 and what? We have 494 joules per kg degrees Celsius. Then for water, we have what? We have 420 joules per kg degrees Celsius. They are saying calculate the what? The mass of steel. Then now, the mass of steel. Then now, the hints that we are given, they are telling us that, let us look here. They are saying whenever we are having 1 liter, we are having how many? 1 kg. Are we together? Then this one takes us to what? To our knowns. Let us look at our slides. We check our knowns. We have our steel. We are requesting the mass. We have our steel, we are requesting the mass. The knowns, we know we know T1, we know T2, we know C, but we want M. Then now, when we are looking at the knowns for what? For water, we know that 1 liter of water is equal to 1 kg of what? 1 kilogram. Then now we know that 1 liter is 30 what? Is 30, 1 liter is what? Is 30. Then our mass, it implies that it would be what? 30 kilogram. Then our T is what? T1 is given, our T2 is given as shown in the PowerPoint slide. Then what do we request? We request the mass of the what? Of the steel. As it is written, we are making M the what? The subject of the formula for steel. Just because of time, you can follow us on Twitter. You can follow us on Facebook, Instagram. We are more than welcome to help you. As for now, thank you. Tune in for the second lesson, which will be electricity. I thank you.